Welcome back to our solutions videos on our fluids questions. This video is going to cover questions 13 and 17. So let's just jump right in. Question 13 asks us, in a movie, Tarzan evades his captors by hiding underwater for many minutes while breathing through a long, thin reed. Assuming the maximum pressure difference his lungs can manage and still breathe is minus 85 mmHg, or millimeters mercury. Calculate the deepest he could have been. So, this problem is fairly challenging. It's kind of weird trying to figure out exactly what it means, but the one thing it does give us, the one bit of real information that we can grasp onto, is that there is something that we need to think about, is this max pressure difference. The max pressure difference, and that is equal to negative 85 millimeters mercury. That is pressure. That is a unit of pressure. And for us, it's not really a useful unit of pressure for our calculations that we're going to be using. So honestly, before we even understand what that means, we know we're going to need to use it. Let's just turn that into a more useful unit of pressure right here, right now. So how can we turn millimeters of mercury into a useful unit? Well, we know how many millimeters of mercury are in an atmosphere. You will be given this, or you can look it up, or you can memorize it, but you should know that there are 760 millimeters mercury in one atmosphere, which is also 1.01 times 10 to the 5th pascals. This is going to be another example where we really want to be focusing on the pascals part. We want to turn this number into a number in pascals. So if we have negative 85 millimeters mercury, we need to multiply that by a ratio that's going to convert this into pascals. So we set up our equation, and we need the unit that we want on top and the unit that we're trying to cancel out on the bottom. So we're going to have 1.01 times 10 to the 5th pascals per 760 millimeters mercury. That way, those units cancel, and we're left with the units of pascals that we want. When we do that, we find that 85 millimeters of mercury is equal to 11,296 pascals. Or we can simplify that and let's just say 1.3 times 10 to the 4th pascals. That'll be good enough for us. And we'll put a negative on there, and we'll figure out what that means now. So what does it mean that he can experience a pressure difference of this? So think about what Tarzan is doing. He is sitting, I was about to draw Tarzan, I don't know. I'm going to draw a box. Here's Tarzan, he's a box now. He's sitting underwater with a tube coming out. Tarzan's lungs function normally at the pressure of an atmosphere. What this is saying is that since his lungs function at an atmosphere, the pressure of his environment can only be greater than the pressure of his lungs by 85 millimeters of mercury, or this 1.13 times 10 to the 4th pascals. So written out, it means that the pressure of his environment minus the pressure his lungs work at, which is the atmosphere, has to be equal to this difference of 1.13 times 10 to the 4th pascals. It means the negative sign means that it's less than, meaning his lungs are at a pressure that is that much less than the pressure outside. So if we want to find out how deep he can be, we need to know that this pressure is that difference. This pressure is where he's going to be functioning. So since we're working with pressure, we should think our pressure equation. So the pressure of the outside environment is going to be equal to rho GH plus the atmosphere. Okay, actually, I'll make that ATM. Well, what we just said was that if we subtract this to the other side, we see that the pressure of the environment minus the pressure of the atmosphere is equal to rho GH. Well, we just said that this quantity here, this is the pressure difference that his lungs can handle. So we want to set this equal to this. That way, we're actually going to be able to figure out how deep he is by solving for H. So if we solve for H, we find that H is equal to P minus PATM over rho G, which we said was 1.13 times 10 to the fourth divided by rho of water. The density of, now this is the density of water because that is the environment that he is sitting in. He's under the water. And the density of water is 1,000 kilograms per meter cubed. We need to use kilograms per meter cubed because our pressure is in pascals. We need the units to match up. Pascals works in newtons, which relates to kilograms, per meter cubed, which, hey, look, or sorry, per meter squared, which is units of meters. So we need to make sure that our other units match up. And gravity can stay at 9.8 because meters per second squared matches up with pascals. So now that we have all of those numbers, we'll plug them in, and we find that he can sit at a density of around 1.15. The book says 1.2, and that's fine. Either one, depending on how you round out. But as long as it's around that value, you're on the right track. So we know that the pressure difference means that is the pressure difference between his lungs at atmospheric pressure and the surrounding environment at whatever it's going to be. So we don't actually care what it is. We just know that the surrounding environment is 85 millimeters of mercury greater than his lungs, or his lungs are 85 millimeters of mercury less than the environment, and that's how he can function. So he can breathe at this distance below the water. Any further and he wouldn't be able to breathe. Now let's move on to question 17. Question 17, still relating to pressure and Pascal's principle, says a house at the bottom of a hill is fed by a full tank of water 6 meters deep and connected to the house by a pipe that is 75 meters long at an angle of 61 degrees from the horizontal. Determine the water gauge pressure at the house, and B, how high could the water shoot if it came out vertically of a broken pipe in front of the house. So question A is pretty straightforward, hopefully. Let's give it a try. So we have a tank on top of a hill, and it has a pipe coming out at an angle which feeds to the house below. The problem tells us that the tank is 6 meters tall and that the pipe is 75 meters long, and it sits at an angle of 61 degrees to the horizontal. So now we know all the properties of our tank and pipe, and it asks us in part A, determine the water gauge pressure at the house. So when it says gauge pressure, remember what that means. Gauge pressure means don't include atmosphere. We don't care about the atmosphere. The house is atmospheric pressure, the tank's atmospheric pressure. We don't need that. What we care about is the gauge pressure without the atmosphere. So we can use the equation, the pressure is equal to just rho GH. This, of course, is the density of water. G is 9.8 meters per second squared. H is the hard part. H is what we need to find. So H is going to be equal to the height of the tank. So we need to find the height of the tank plus the height of the pipe. So your first instinct might be, okay, let's just add 6 to 75, but you got to be careful about that. 75 meters is not the height of the tank. We need the actual height of the fluid above the ground point. And the pipe does not sit 75 meters above the ground. It sits a little bit less than that. We need to find this vertical component of that 75, because that's going to tell us the true height of the tank. So remember our trig. We have SO, Ka, Toa. We have our angle here. We need to use sine. So sine of our angle is equal to opposite over hypotenuse which in this case is going to be that height of the pipe that we're looking for, divided by 75 meters. So the height of the pipe is equal to 75 times the sine of our angle. So our height is equal to 6 meters for the tank height, because that is full of water, plus the pipe height, which is 75 times sine of 61 degrees, and that's going to get us 6 plus 65.6, roughly. Again, depending on how you round, you might have a slightly different answer, but it's going to get us about 71.6 meters. Now, for part A, we can plug that into our equation, and our pressure is equal to rho, the density of water, which is 1,000 kilograms per meter cubed. Again, we're using meters here because our height is in meters and gravity is in meters per second squared, times 9.8 meters per second squared, times the height of 71.6 meters, and that gets us a pressure of quite a bit, 701,645 pascals, depending on how you round, or 7.02 times 10 to the 5th pascals. It's quite a bit. That's actually a lot more than atmospheric pressure, over 6 times more, not quite 7. So it's a lot of pressure. And in part B, now this one's a little bit tricky. I think we'll get a better handle on why this is the case when we talk about Bernoulli's principle. But for now, we can ask this question, and we can use a little bit of our reasoning skills to answer it. How high will the water shoot? It's actually the obvious answer. We have to think about conservation of energy. There's a whole lot of water providing a force underneath. Well, we can't shoot that water to higher than where it started, because that would disobey the laws of conservation of energy. It started at a certain height. We can't bring it back to higher. We would gain energy. But if we're assuming a perfect system, which with most of these physics problems we are, it's not going to go less because it didn't lose any energy anywhere either. So the answer to this is actually it goes back up to the full height that it started at. So this goes up to that full height of 71.6 meters. It returns to its original height because energy is conserved. Again, we will see that we will be able to prove that a little bit more precisely or explicitly when we talk about Bernoulli's principle, but it truly does return to that original height that it was at until the water level starts to decrease. Then it would only return to the max height of the water. So returns to max height of water. So for us, that first bit would go all the way up to the 71.6 meters. That's a lot of pressure pushing it up there, but it can be done. So please check out the next video for problems 23 and 25. See you then.